Hello students, today we will solve question number 5, and the question number 5 asks us about determine the electrostatic potential energy of a system consisting of two charges 7 microcoulomb and -2 microcoulomb and with no external field placed at -9 centimeter 0, 0 and 9 centimeter 0, 0 respectively. How much work is required to separate the two charges infinitely away from each other? Suppose that the same system of charges is now placed in an external electric field of E equals to A upon 1 by R square, where A equals to 9 into 10 to the power 5 Newton per coulomb meter square. What would be the electrostatic energy of the configuration? So, in the first case, they have asked us to find the electrostatic potential for what? When there is no external electric field, E external equals to 0. Second, in B part, they have asked us the amount of work done to separate these two charges infinitely away, okay. And in the third, they have asked us to find again electrostatic potential, but in this case we have external electric field which is equal to A into 1 by R square. Okay, so the given information in this question to us for the ease of solving this is that we are given with the two charges Q1 and Q2. Here Q1 equals to 7 microcoulomb, which is equals to 7 into 10 to the power minus 6 coulomb, and Q2 equals to minus 2 microcoulomb, which is equals to 2 into 10 to the power minus 6 coulombs. Then the distance between them is, this is our origin, this is our x-axis, and we consider that origin is at point O. From point O 9 centimeter away is charge Q2, and from O 9 centimeter before is charge Q1, 9 centimeter. So here this is given as minus and here this is given as the plus. So the overall distance between the two charges, distance between Q1 and Q2 is 9 plus 9, that is 18 centimeter. And this 18 centimeter can be written as 18 into 10 to the power minus 2 meter. Okay, so this is the information we have. With the given information, we have to proceed to find the electrostatic potential when external field is 0. Work done to separate these two charges by infinitely away distance, and the third one, electrostatic potential when there is external field of magnitude A into 1 by R square. So let's proceed to find the solution for the given problem. Now see the solution over here. We are given Q1 7 microcoulomb, Q2 minus 2 microcoulomb, R1 minus 9 centimeter away and R2 9 centimeter away. So the total distance is 18 centimeter. For our potential energy to be found, what we do is we write it as Q1 Q2 divided by 4 pi epsilon naught into R. The charges under consideration, the proportionality constant and the distance between the two charges. So Q1 is given by this term, Q2 is given by this term, and this is the value for our K, and the value of the K is 1 by 4 pi epsilon naught, and this is the value for distance in meter. The distance between two charges Q1 and Q2 in meters, So the answer which we get for the U is U equals to minus 0.7 joules, minus 0.7 joules. So this is the potential energy in the absence of external electric field. Now we will go to the point B, where we need to find work done to separate the two charges infinitely away from each other. Infinitely away from each other implies that at infinity there will be some potential energy. Here there is some potential energy. So we have to give that much of potential energy from the point A, at point A and at point infinity. Okay, we have to give potential energy to the charge in such a way that this charge overcomes the force of attraction due to the other charge and moves away and infinitely away from our charge 1. So how much is that energy will give us the work done. The work done equals to change in the potential energy, that is potential energy at infinity minus potential energy at a given point where our charge is present. It can be point 1, it can be point 2, so we will take it as a point A. Okay, so at infinity what is the potential energy? Basically, to understand all these electrostatic systems, we have considered that in like question number 3 also we have seen, and here also we have considered our potential energy at infinity to be 0. Potential energy at infinity to be 0, taking it as 0 minus UA. At position A, what was the energy? See over here, we have found out the energy to be minus 0.7 joules. So minus of minus will be plus and answer will be 0.7 joules is the amount of work to be done on the system of charges to separate them infinitely away from each other. This is the amount of work. That much energy externally should be provided to the system of charges to separate them infinitely. Okay, now moving on to the C. Previously what happened was that these Q1 and Q2 were not bound due to any external electric field. No external electric field. But now these two charges Q1 and Q2 are under a external electric field. Now what is here difference is that only the externally these charges will face some sort of force, but internally between these two charges the mutual interaction will be same. These will remain unchanged. relation of Q1 and Q2 will remain unchanged, will remain same. Okay. System of charges are separated by a given distance are now placed in an external electric field E equals to A 1 upon R square. Here the value of A is given by 9 into 10 to the power 5 Newton per coulomb into meter square. We have to find the electrostatic energy in this system. In the given system we need to find the electrostatic energy. The mutual interaction energy of the two charges will remain unchanged. In addition, there is the energy of interaction of the two charges with the external electric field. This external electric field will interact with charge Q1 and with charge Q2. So, this is what we are getting, the interaction of charge Q2, interaction of charge Q1. So, we will write it as this: A into the potential at A at like Q1 into V of R1. So that will be like our energy is A into 7 microcoulomb upon 0.9 centimeter. 0.9, it's written little wrong. It is not centimeter, it's meter. 9 is in centimeter. 9 centimeter, and if it is considered in the point, it should be 0.09 meter. So here it is in meter. Please do the needful correction over here. This is not centimeter, this is meter. It is written by mistake. Similarly, for Q2 we are having this particular value. Now the net electrostatic energy is energy due to Q1, just a minute. Energy due to Q1 plus energy due to Q2 plus the energy we have seen when there was no electric field, the energy between Q1 and Q2, energy between Q1 and Q2, the mutual energy of these two charges. For this we will come from here, for this we will come from here, and this will be from the previous slide, from the subset A. We will find the value from subset A. What is the value for that? It was minus 7, it was minus 0.7 joule. Minus 0.7 joules. So, we have got A into 7 microcoulomb by 0.09 meter plus A into minus 2 microcoulomb into 0.9 divided by 0.909 meter minus, because this is minus, though we are adding, but because here the sign is minus, it is converted into the minus 1, minus 0.7 joules. So after solving this we get 70, after solving this we get 20 minus 0.7 joule. This is minus, so this sign will also convert into minus, and 70 minus 20 is 50, 50 minus 0.7 is 49.3 joules. So when there is external electrostatic field, the amount of electrostatic energy that is needed is 49.3 joules. Now I will explain you how do we get this particular calculation of 7 microcoulomb by 0.09 meter. Okay, we got A into 7 microcoulomb divided by 0.09 meter. 7 microcoulomb can be written as 7 into 10 to the power minus 6 coulomb. Let us substitute. Then the value of A is given as 9 into 10 to the power plus 5. Let us substitute. So it will be 9 into 10 to the power 5 into 7 into 10 to the power minus 6 divided by 0.09. We will remove this dot, and as we are removing this decimal, on the numerator side we have to multiply by 100. So this 9 will get cancelled with this 9, and this power of 5 and this power of minus 6 and this power of 2 will be given as 7 into 10 to the power plus 5 minus 6 plus 2. So it is 7 into 10 only, and hence we will get 7 joules. Similarly, I will solve in the provided here space. Similarly, the other one, A into 2 minus 2 coulomb microcoulomb divided by 0.09. Here A is 9 into 10 to the power 5 minus 2 microcoulomb can be written as minus 2 into 10 to the power 6 divided by 0.09. Removing the point, we need to multiply numerator by 100. 9 and 9 will cancel out. The amount we are left is minus 2 into 10 to the power 5 minus 6 plus 2. Hence the answer we got is minus 20 joules. So that's how we got this particular value of 70 and 20. We have substituted the values and converted the microcoulomb into the coulomb, and when we are subtracting, 70 minus 20 is 50, and then 50 minus 0.7 will be like 9 here, 4 here, 10 here. 10 minus 3 is 10 minus 7 is 3, 9 minus 0 is 9, 4 minus 0 is 4. So we got 49.3 joules as the electrostatic energy when the external electric field is introduced into the system. Okay, so this is how we have solved the question. So that's all for the today's class. We'll meet in the next class with a new topic. Have a good day. Bye bye.